From the dim, cavernous hangars of military airbases to the vast, open skies, the V-22 Osprey presents a stark paradox. It is an engineering marvel, a revolutionary tiltrotor aircraft capable of vertical takeoff like a helicopter and high-speed cruise like a turboprop plane. Yet, its operational history is marred by continuous mechanical failures and devastating crashes, casting a long shadow over its groundbreaking design. Our investigation delves into the technical heart of this machine, examining why such an ambitious fusion of flight modes has inadvertently engineered a legacy of persistent unreliability. We'll probe the hidden complexities, the unseen stresses, and the relentless battle for mechanical integrity. The V-22's core innovation lies in its tiltrotor design, a concept first conceived to bridge the gap between helicopters and fixed-wing aircraft. This enables it to perform vertical takeoffs and landings, crucial for operations in confined spaces, then transition its massive prop rotors to a forward-facing position for efficient, high-speed, long-range flight. This dual capability was envisioned to offer unparalleled tactical flexibility, particularly for the U.S. Marine Corps and Special Operations Forces. However, it's precisely this groundbreaking hybrid nature that introduces a layer of engineering complexity rarely seen in aviation, creating a host of unique and profound challenges. The ambition to combine two distinct flight regimes within a single airframe naturally escalates engineering demands. According to a 2011 Government Accountability Office (GAO) report, the V-22 Osprey possesses over twice the number of dynamic components of a conventional helicopter. This statistic is critical. Each additional component, especially within a highly stressed dynamic system, represents another potential point of failure. The sheer volume of intricate parts, gearboxes, and control linkages required to facilitate the tiltrotor's transformations and power transfer pushes materials science and mechanical engineering to their absolute limits, demanding unprecedented levels of precision and reliability from every single element. At the core of the V-22's mechanical issues lies its complex powertrain. Power from the two Rolls-Royce AE1107C turboshaft engines is delivered to the prop rotors through a sophisticated drive system. This includes interconnected nacelle gearboxes, a wing-spanning driveshaft, and a combining gearbox (CGB) that can transfer power from one engine to both prop rotors in an emergency. It's a marvel of redundancy and power management, yet it's also a recurring source of critical failures. These highly stressed gearboxes, operating under immense loads during transitions and sustained flight, have proven to be a persistent vulnerability, necessitating frequent inspections, costly replacements, and contributing significantly to the aircraft's maintenance burden. Among the specific mechanical issues, the clutch heart engagement or CHE phenomenon stands out as particularly critical. This occurs when the prop rotor gearbox's one-way overrunning clutch mechanism engages abruptly during flight, often during transitions between flight modes. The sudden engagement can transmit immense shock loads back into the drivetrain, potentially causing catastrophic structural damage to the gearbox and even leading to engine failure. The Marine Corps V-22 Program Office acknowledged this as a significant concern in 2022, underscoring the severity of this unpredictable event that has prompted multiple fleet stand-downs and intensified engineering investigations to identify and mitigate its root causes. The inherent complexity of the V-22 Osprey translates directly into a formidable maintenance burden. Compared to the legacy aircraft it was designed to replace, the V-22 consistently demands significantly more maintenance man-hours per flight hour, MMH/FH. A 2010 Naval Air Systems Command (NAVAIR) assessment, corroborated by internal military reports, indicated V-22 MMH/FH figures frequently exceeded 20 to 30 hours. This is dramatically higher than the 8 to 12 MMH/FH typically required for older platforms like the CH-46C Knight. This disparity highlights the intensive labor, specialized tooling, and extensive spare parts logistics necessary to keep the V-22 fleet operational, impacting readiness and operational costs across the board. Beyond inherent design complexity, the V-22's demanding operational tempo and harsh environments further exacerbates its mechanical vulnerabilities. Extensively deployed in high-dust, high-heat regions like Iraq and Afghanistan, the aircraft's sensitive components, particularly its gearboxes and avionics, endure extreme wear and tear. Field maintenance reports consistently indicate accelerated degradation of parts due to abrasive sand, elevated temperatures, and the relentless stress of combat operations. This combination of an already complex design and the rigors of real-world deployment creates a compounding effect, pushing the limits of durability and reliability, often leading to unscheduled maintenance and component failures far sooner than anticipated. The V-22 Osprey relies heavily on a sophisticated fly-by-wire flight control system to manage its complex aerodynamic forces, especially during the critical transitions between helicopter and airplane modes. Unlike a conventional aircraft with direct mechanical linkages, the V-22's controls are entirely electronic, interpreted and executed by multiple redundant computers. This digital brain must precisely coordinate the tilt of the nacelles, propeller pitch, and control surfaces simultaneously. Any software anomalies, sensor discrepancies, or latency in this system can introduce instability, posing significant challenges. An independent FAA review of tiltrotor technology highlighted these software and integration complexities as paramount to flight safety and operational reliability. The V-22's journey from concept to operational asset has been exceptionally long and expensive. The program initiated in 1981, aiming for a revolutionary military transport. However, it only achieved initial operational capability in 2007, a full 26 years later. This protracted development was riddled with technical hurdles, design iterations, and budget overruns. Congressional Budget Office (CBO) reports indicate development costs have exceeded $35 billion, with the unit cost per aircraft climbing from an initial estimate of $20 million to over $70 million. This contrasts sharply with the development trajectories of many conventional military aircraft, underscoring the extraordinary financial and engineering investment required to bring such a complex, novel design to fruition. The V-22's development was tragically punctuated by a series of high-profile crashes, particularly in its early testing phases. These incidents were critical, often fatal, and highlighted fundamental design flaws and operational challenges. Notable crashes, such as those in 1991 and 2000, led to significant program delays, redesigns, and intense scrutiny from safety boards in Congress. Each accident, while devastating, provided invaluable, albeit hard-won, data for engineers to refine the aircraft's systems, from flight controls to hydraulics and structural integrity. These early setbacks undeniably shaped the V-22's evolution, underscoring the steep and often unforgiving learning curve associated with revolutionary aviation technology. Evaluating the V-22's safety record requires a dispassionate look at the numbers. Since its first flight in 1989, Department of Defense safety records indicate the V-22 program has recorded at least 16 major hull loss crashes, resulting in over 50 fatalities across both development and operational phases. Comparing mishap rates, the MV-22 variant exhibited a rate of 3.97 per 100,000 flight hours from 2007 to 2017. While these figures represent a complex safety profile, they are notably higher than some conventional fixed-wing transport aircraft, sparking ongoing debate about the aircraft's inherent risks versus its unique capabilities. These statistics underscore the critical challenges of operating and maintaining such an advanced, complex machine. The V-22's unique flight envelope demands significant aerodynamic trade-offs. The large prop rotors, essential for vertical lift, become drag-inducing elements in forward flight, necessitating their tilt. The transition itself creates complex and unpredictable aerodynamic forces. During this critical phase, the aircraft operates in a vortex ring state for a brief period, an aerodynamic phenomenon that can severely reduce rotor thrust and control authority, a condition often associated with helicopter accidents. Managing these forces dynamically, especially during high wind or low-speed maneuvers, is a constant challenge for the flight control system, requiring precise sensor inputs and rapid computational adjustments to maintain stability and safety. The large, flexible prop rotor blades of the V-22 are subject to immense and constantly changing dynamic loads. These forces manifest as complex vibrations and stresses that propagate throughout the entire airframe. Managing these rotor dynamics is critical. Imbalances or resonance can lead to structural fatigue, accelerated wear on gearboxes, and even catastrophic failures. Engineers employ sophisticated vibration analysis and dynamic balancing techniques, but the very nature of a large, tilting rotor operating at varying speeds and angles presents persistent challenges. Microscopic cracks, undetectable without advanced diagnostics, can propagate under these unseen forces, eventually leading to component failure in high-stress areas. To withstand the unique stresses of the V-22's tilt rotor operation, engineers have pushed the boundaries of material science. The aircraft extensively uses high-strength alloys and advanced composite materials in its airframe, gearboxes, and prop rotors. These materials are chosen for their exceptional strength-to-weight ratio and fatigue resistance. However, even these cutting-edge materials have limits. Components are subjected to extreme heat, cyclical loads, and abrasive environments, accelerating material fatigue. Microscopic flaws or manufacturing imperfections can become critical points of failure over time, despite rigorous quality control. The pursuit of lighter, stronger, more durable materials is a continuous, essential battle in maintaining the Osprey's operational integrity. The V-22 Osprey represents an extraordinary financial investment, not just in its initial procurement but in its ongoing maintenance and upgrades. As cited by Congressional Budget Office reports, the unit cost for a single V-22 has reached over $70 million, with the total program development costs exceeding $35 billion. These figures do not fully capture the continuous expenditure on fleet-wide reliability improvements, spare parts inventory, and specialized training for maintenance personnel. This substantial financial commitment underscores the strategic importance placed on the Osprey's unique capabilities, even as it highlights the inherent cost of pushing the boundaries of aviation technology and managing the complex failures that arise. Despite its troubled past, the V-22 program is defined by relentless efforts to enhance reliability and safety. Significant engineering resources are continuously invested in upgrades and modifications. For instance, in 2023, the Marine Corps initiated a comprehensive program to replace critical gearboxes and improve clutch mechanisms, directly addressing some of the most persistent failure points. According to an Aver press release, these upgrades aim to enhance the aircraft's overall reliability by 20% over the next 5 years. This commitment to continuous improvement, integrating lessons learned from operational experience and technical analysis, demonstrates the military's dedication to mitigating the inherent risks and maximizing the operational lifespan of this complex aircraft. Given the V-22 Osprey's documented challenges, a fundamental question remains: why do military forces persist in its deployment? The answer lies in its unique, unmatched mission versatility. No other aircraft can currently combine the V-22's speed and range with its ability to conduct vertical takeoffs and landings in austere environments, far beyond the reach of conventional helicopters. It offers crucial advantages for troop insertion, cargo delivery, and special operations, fundamentally altering tactical possibilities. This operational edge, despite the substantial mechanical and financial costs, continues to make the V-22 an indispensable asset for commanders, defining its continued, albeit complicated, presence in global military fleets. The V-22 Osprey stands as a potent symbol of aerospace ambition, a revolutionary machine that dared to defy conventional aviation limits. Its continuous mechanical failures and tragic incidents are not merely defects, but inherent consequences of pushing technological boundaries. They represent the exacting toll of engineering complexity, the rigorous demands of operational realities, and the difficult trade-offs between capability and reliability. The Osprey's story is a profound lesson in the real-world costs of innovation, reminding us that even the most visionary designs must ultimately contend with the unforgiving laws of physics and the relentless march of metal fatigue. Its future remains a testament to both human ingenuity and the enduring challenges of complex engineering.